Okay. Now,
Yeah, Fred, go ahead and click on the present now.
there we go. Okay. So I'm going to give you a bit of a history lesson.
Fred, yeah, it's now coming. It was not coming before. Now you can start.
Okay. So I'm going to give you a bit of a history lesson, and in this particular case, it's personal. I'm telling you about my life for the last, 30 years. When I first got involved in the IETF, I was in the process of building a router from scratch and designing a routing protocol and kind of doing important things to have a router in the time. And in the time, that meant that it had to support several instances of the Xerox networking, Xerox network system. I'm hearing a lot of noise. Is there a problem on the line? Okay. So at any rate, I worked at a company that built what today we call Ethernet switches, and then I changed companies and went to work for a small router vendor. And so I had customers calling me up and telling me that they had problems in their networks, and could I please do something about whatever problem they described. And so I just, I'm just a mere engineer. I write code, I make it happen. And so I needed to learn an awful lot about how networks behave and what happens kind of behind the scenes. And so I started reading RFCs, and I started reading ACM transactions on networks and ACM SIGCOMM and other industry publications, which were all kind of new to me. And I was just trying to figure out what was going on and how I might fix problems that my customers were having in their networks. One of the first documents that I read was written by a fellow by the name of John Nagel, who was in 1984 a network operator at Philco Ford. And he had a network that was built out of fuzzballs. And the primary thing that he ran on his network was Echoplex terminal controllers. And there were a few guys on his network that had some awful thing called a Sun workstation, and they made crazy things happen in his network. And so he was looking at his code and trying to figure out what one might do about problems, and realized that there was a behavior which was extremely predictable, and when of course there's going to be a problem there, and that is that every time one of his terminal server users would type a character, the character would get put into a buffer. They would build a TCP header, they would build an IP header, they would add an Ethernet header, and they would fire it out the door. And then the person would type the next character, and this would all happen again. And so every character that somebody typed resulted in a packet of 64 bytes on the network. And of course, there were going to be problems because everybody was madly typing. And he said, well, gee, what if we do something really imaginative and we put 2 characters in the same buffer? And it helped. And so if you look in the TCP drivers in Unix, you'll find something called the Nagel option, and this is where it comes from. And so I'm starting to read through RFCs and look at where people have been and what problems they've encountered and what fixes they have thought about a year later, he wrote RFC 970 on packet switches with infinite storage. And now the issue there was that the fuzzball had a grand total of 64K of memory, and it had 8 buffers. Count them, 8 buffers. And people would all kind of stand around and say, gee, wouldn't it be nice if memory was cheap and we could actually put more memory in these things, because then, you know, life would be better because we could have more buffers. And so he asked himself, well, what happens in the logical extreme if I say, fine, I now have an infinite amount of memory, I have an infinite amount of buffer, what happens next? And he predicted at that point something that hadn't actually happened yet, but which was the congestive collapse of the NSF net, the internet at the time, because of problems in the IP protocol, which, okay, we went around and we fixed. So, and in that, he came up with a really very interesting idea. He said, what if I bundled packets together by source address? And said, okay, I'm gonna, if I get a whole lot of packets that have the same source address, I'm gonna make them wait, let other things go through, and kind of send these things through as a class over a period of time, which allowed him now to resolve some of the issues on his network and resolve an issue that he had with the Sun workstations. Now, at the same time, there was a doctoral candidate. I don't think he was working at Xerox yet. I think he was working, I think he was at Stanford, by the name of Van Jacobson. And by the way, there's a lot of people around that have Van in their surname, like Rod Van Meter, who's the chair of a research group in the RTF. In this case, Van is actually his first name. So you'll hear people talk about Van Jacobson as if Van is part of his surname. It's not. His name is Jacobson. And what he was looking at was how can I make TCP work efficiently across the 56 kilobit NSF net backbone, which had all kinds of congestion problems. And so he came up with, at that point, some of the basics of what we now think of as normal TCP congestion control. And then some other people kind of keyed off the stuff about queuing in RFC 970. So Scott Schenker was at Stanford. I think Keshev was there as well. I don't know where Demers was. But they sat down and looked at this concept of what we now call, or what we later came to call, fair queuing, and wrote a paper about that in the Communications of the ACM, which I read and said, well, gee, what if I implemented that in my equipment? I could solve my customers' problems. This is really cool. So Vitalink actually wouldn't let me do that, but when I went to ACC, they let me do that, and so I did one of the early fair queuing implementations in a commercial router. And it was based on this paper that I read in Communications of the ACM. Now, in the course of that, I'm sitting with various other people in the industry and trying to talk about congestion control. And Alison Mankin tapped me on the shoulder, and she said, Fred, so what is your problem with having the host be in control of congestion control? You seem to think that might not be a complete solution. And I said, well, I don't think that's a complete solution. I think the host can certainly help, but it doesn't know enough about what's in the network in order to counter what the network's doing. And I think that was a completely new thought to her. A few months later, she published a paper in SIGCOMM called Random Drop Congestion Control, in which she basically said, well, what if I just kind of occasionally dropped a packet? What would be the effect? And in simulations, she was able to demonstrate that sometimes that was a good thing to have happen. So that this concept of drop control came in there. Now then, 1993, there was 1993 and then 1995, a pair of papers. I'm skipping one here, but okay, I'll talk about Perrick and Gallagher first. Perrick was a doctoral candidate at Stanford. Gallagher was his professor. One of the problems that was going on in the industry was if you talked to the telecom guys, they would say, well, obviously, the host can do whatever it wants, so we're going to control things in the network, and the network will make everything work wonderfully. And the people on the host, people like Van, Kathy, and so on, would kind of say, oh, we'll control that from the host, and frankly, we'll do a better job. And so Perrick sat down and did a control theoretic proof, looked through the basically both arguments, and was able to prove that in order to control congestion in a network and to be able to have a predictable round trip delay on a packet, you had to do both. You had to have control of how much any particular host is keeping in the network. And so that would be done from the host. And then the network needed to act in a predictable fashion with that load, which turned out to be, that was a very important result. Now, let me back up one. So 1993, also in 93, Transactions on Networking, Van Jacobson and Sally Floyd published a paper called Random Early Detection Gateways for Congestion Avoidance. And what they were looking at was, could they figure out a way to use drop policing to intelligently interact with data flows and make TCP do the right thing. Sally eventually also worked on UDP, but at this point she's only thinking about TCP. So if you look at Cisco equipment and you see something called WRED, I wrote that, and this is the paper it came from. So there's actually a really good overview of this, all this stuff, which I won't go through, but it's a talk that Van gave at Xerox Park, and there's the URL there. Okay, so what was the early research in adaptive queue management and congestion control? These certainly weren't the entire list of papers, but they were. You call this RFCs we love. These are RFCs that I love. You know, these were important comments that were made in the course of figuring out congestion control. Now, in the IETF, we started working on the concept of congestion control. It started out with a paper written by Scott Schenker, who was on the random early detection paper, John Roklowski, who was with MIT, and somebody else, I forget who. RFC 1633 was basically trying to bring together what they had learned, or what research had learned up to that point about applications behavior, and it defined two terms, which turned out to be fairly seminal. So we talk about applications that use TCP or QUIC or other things like that as elastic applications. They adapt themselves to the network. And then voice and video and a number of IoT applications are essentially real-time applications. They don't adapt themselves to the network. You have to design with them in mind. So these definitions were given in that paper. And the next thing was that, well, we had a bunch of TCP implementations around, and frankly, they didn't work well with themselves, much less with each other. And so Vern Paxson got a group together and started bench testing the different applications using TCP. And then in the IETF, he would name and shame the bad ones, and they were all bad ones. So he's saying, so I looked at this from Microsoft and that from Sun and whatever, and talk about the problems that they were encountering with TCP. And the net effect was that the companies went back and the different implementers, some of which were open source, went back and looked at their implementations and fixed them. And so we wound up with TCP that actually worked across a real network. Now, there's been a lot of work since. I think I counted 177 RFCs that describe TCP, this, that, and the other. And there's a lot of academic papers that have been written in end-to-end and ICCRG and in the IETF TCPM. Perhaps the most important one there is RFC 5681, which describes Unix BSD TCP Reno. And Cubic, of course, is different, and that's entirely academic. But that's kind of the documentation of how TCP more or less works today. So we did a bunch of work over a period of, I don't know, 8 years, 10 years in the IETF, working on congestion control there. And in the course of that, now Dan Jacobson is married to Kathy Nichols, and Kathy said, listen, let's get together a working group and figure out how best to use congestion control things in the network. Okay, so I'm going to have to go back to that other one. And so we had designed a quality of service architecture called the integrated services, and involved a protocol that you could basically go to the network and build something similar to an ATM virtual channel, ask the network to set aside bandwidth for some real-time session or application. Turned out that that wasn't widely deployed. The service providers didn't like it. But then Kathy's work was on differentiated services. So that wound up as a way to identify sessions that were happening, applications in the network, and then to describe what one wanted the network to do in terms of queuing and drop policy and that kind of thing. Now, in terms of implementation, I implemented it in Cisco equipment. I know it's been implemented in a number of other places. Turns out that this is not heavily used in IP networks, but it's very heavily used in MPLS networks. So IP quality of service stuff tends to be within a network as opposed to between networks. But there is kind of an interesting paper. If you look at RFC 8100, this came from T-Mobile, from Deutsche Telekom. And the concept that Rudiger Gieb is working on there is that they wanted to build services that would cross multiple ISPs. And so he basically picked the kinds of things that one did in MPLS networks, figured out how to replicate that using DiffServ in IP networks, and documented that. So that's RFC 8100. So that's IETF work. Now, if I look at differentiated services, kind of look at DiffServ and say, what does it really talk about? What it defines is add an interface, and you can do this on an incoming interface. I'm receiving traffic from something else, or on an outbound interface where I'm sending traffic to something else. what I do is I have a stream of traffic coming from wherever it's coming from, and I put it through some kind of logic that will look at the diff-serve code point and potentially look at other information in the packet and say, what is it? And then having decided what it is, it would put it in. You can do this with a calendar queue, or you can do this with separate queues, kind of whatever way is appropriate to your hardware. But it'll put the thing into a class or a queue. And then we have a technology, an object that we call a scheduler. The scheduler, by some rule, then takes packets out of those queues and sends them on their merry way. Now, there's a number of different possible schedulers. You can talk about a Fifo scheduler, which simply says packets in, packets out, and away they go. You can talk about simple priority, in which I've got several classes or several queues, and if there's something in one of them, I'm going to send that next. If there isn't any traffic there, then I go to the next, and so on. So simple priority. And then you can get into fancier queuing systems. In Linux, I believe you have something called a class-based scheduler, which is essentially a weighted round robin system and allows you to take several streams of traffic coming through and interleave them to some extent. And then kind of the general processor sharing model is in weighted fair queuing, and you can do a similar thing, but now you can be somewhat more detailed. And then now the other obvious thing to do is, suppose instead of saying, I just want to make the packets get out of each other's way, which is what WFQ does, suppose I said, well, what I want to do is make some class or all of the classes proceed at a certain rate. So I might literally have a bunch of traffic come into queues, and then I'll send whatever I'm going to send, and then I'm going to wait until the next time interval comes, and then I'm going to send some more. And so Alicia Zhang came up with the term work conserving and non-work conserving for that. So traffic shaping becomes a non-work conserving discipline. But this is basically a picture of differentiated services, what the bits and pieces are and how they work. Now there's been other work since then. A lady by the name of Feng at MIT, which is Chinese, came up with adaptive red and then flow red, which is random early detection applied to a data flow. And so adaptive red is actually implemented in Linux. In the course of the AQM working group in the IETF, kind of the successor of differentiated services, then Van and Kathy brought in Codel, which that's coming from open source, and Ron Pan from Cisco brought in the proportional integral controller enhanced Pi. And Mohit's going to talk about those two, so I won't go into them in detail. But those are, we've learned some over time, and these are attempts to do the job better. Ron Pan was basically trying to fit a differential equation to the data flow of packets, and then figure out how to manage that differential equation. Codel is more about managing delay and just trying to minimize the delay that things experience. Now, in the course of this, you'll notice I've mentioned queuing. I've talked about weighted fair queuing and class-based queuing and so on. And I've talked about drop policies. In the differentiated services architecture, we can apply both those to a problem, and quite often do. So that winds up looking something like this. I might have a FIFO queue, or I might have a number of FIFO queues or something that acts like a bunch of FIFO queues for the scheduler, and then apply a drop policy to individual queues or to parts of the queuing system. And so, as I use these things and as I configure them, I actually wind up working with them together. And there is a formal description of that. It's at least in the Internet Draft. I think it's in an RFC, which describes what's called fair queuing with coddle and fair queuing with pi. So what you're doing now is you're applying coddle or you're applying pi to individual data streams moving through a fair queued interface. And once again, Mohit's going to talk about that, but I just want to put this there as, yes, one can do that, and that's one of the things that we think about in this context. So RFCs we love. I found myself just taking a course in reading and learning something about the networks that my customers were operating in, and turning around and implementing them in Cisco equipment at the time, because I worked for Cisco, or at ACC, which is where I was before Cisco. And that turned out to be very, we learned an awful lot about how this behaves in real networks as a result of that. So now, Drew, let me turn this back to you. Do you have questions or thoughts?
Thank you, Fred, first of all, for giving us such an educative history of how this whole thing started. We are running a little bit behind. So what we'll do is let's have Mohit present, and then we can take the questions for both the history part and focusing on this together at the end. Does that work for anyone, or does anyone has any specific question that they must ask right now, maybe more related to basic?
Dhruv, Dhruv, this is Kannan. I have a quick question for Fred.
Yeah, go ahead.
So, Fred, you talked about TCP congestion control. And I think a couple of years back, Google published a set of drafts on BBR. So I just want to know what's the state of that. Is that something that is being adopted or deployed?
As far as I know, Google's doing it and nobody else is.
Oh, okay.
Thank you. Let's have Mohit's presentation, and then after that we'll have maybe a combined Q&A for both Fred and Mohit. Mohit, would you like to present now?
Yeah, sure. So just let me know when my presentation starts appearing.
Yeah, it's on now. You can go ahead.
Okay. Is it visible clearly now? I just maximized it.
Yes, it is. Yes.
Okay, thank you. Hello everyone. I am Mohit. I work as an assistant professor in Department of Computer Science at NITK Surathkal. First of all, thank you very much for having me here. I have chosen a topic on the QoS, basically the problem that's related to the queuing delays, the problem that happens due to the surplus buffering. And I'm just going to continue from where Fred actually mentioned about CODAL and Pi. I'll be discussing both of the queue management algorithms, which are relatively recent. As you can see from Fred's presentation, there have been lots of queue management algorithms since so many years, but then these have been the new ones that everybody has been discussing at IETF, and both of them have made their way to RFCs. So I'll just give a brief about both of them and some bit of work that we have done here in my institute with my PhD students about CODAL and Pi. So just to set the context right, I'll just start with the highlighting what are the performance requirements that our modern internet systems have. and then go about describing the problem, which we popularly know as buffer bloat today, and also talk a bit about reactive congestion control, which Fred already mentioned a bit about, and then talk about the AQM algorithms in detail. And finally, I would leave a couple of slides for everyone, so that if in case somebody wants to try these things, which tools are relevant and where are they available and how can we get started with them. So just some small pointers in those directions as well. So basically, we have known always that latency is something that a packet needs to travel from a sender to receiver, but it has actually 4 main components, which we see here in my presentation. So we know of propagation delay as the time that the packet needs to travel, which depends on the distance and the speed of the signal propagation. We have transmission delay, which is something that gets affected based on the data rate that we have. So it's a function of the packet's length that we are transmitting and the data rate that we have. And processing is about inspecting the packet headers, checking for bit level errors, finding out where to send the packet, doing all the routing stuff. It includes processing delays. But the most important thing that I'm going to cover in this presentation is about the queuing delay, where the packets spend time in the queue until they are forwarded. So before we go into the queuing delay aspect, why this whole latency thing has been an important concern these days is primarily because most recently we were all focusing upon getting more throughput. Even if you look at the Wi-Fi standards that came in, they were named as, for example, 802.11n was named as high throughput. And then we called as very high throughput. We called it as VHT in the IEEE standards. But now there has been standard which is called high efficiency. The way this word high efficiency has been coined is that the emphasis is not just on getting very high throughput, but it's also on getting ultra low latency. So it was realized that just adding more bandwidth is not always going to give us an ultra low latency. So this is something that I quote from Ilya Grigoryk's book, from High Performance Browser Networking, where he talks about the fact that bandwidth matters, but it doesn't matter much, particularly for applications. For example, if you are loading just a Yahoo homepage or a Google homepage, which is not actually limited due to the bandwidth, but it is limited due to the latency. So this is a plot which I found in his paper based on the experiments that they have done. You can see that if you have a 7 megabits per second data rate, or you have a 10 megabits per second data rate, the latency, the page load time doesn't significantly vary. So just adding more bandwidth, of course, is useful for other applications such as streaming an HD video or having file downloads, but adding more bandwidth will not reduce the latency by a lot. So there was something else that we need to do to actually cut down the latency. And that's the whole point about this. So we have always categorized latency into 3 different classes. We call them as latency sensitive traffic. And the examples is about the VoIP or the audio video conferencing, online games that are becoming very popular, the remote health monitoring services, or the IoT-based home automation services. Then there's another application which is completely different, which is called latency tolerant. We call them as elastic or non-critical traffic in terms of time, which includes huge file transfers or our emails with attachments, or OS updates, app updates, and so on and so forth. And then we have the streaming content, for example, services like Netflix. And all of these have different latency requirements. So there's a nice classification provided in one of the papers that talks about implementing the AQM algorithm at the home router. This is a paper from Swinburne University in Australia, where they have mentioned the type of the traffic on the left and how much delay can these applications tolerate on the right. And they have categorized these applications depending on whether they belong to an interactive class of applications or whether they belong to a timely traffic like streaming, or maybe non-critical, for example, bulk downloads. You can see the voice and video applications or interactive apps, basically, or search queries that we have, all of them, they belong to a category called interactive traffic, and they have latency tolerance only up to about 150 to 200 milliseconds. So when you have so many components adding to the latency, right from the propagation delay to the queuing delay, if any one of those components is having a significant impact, you would see these applications getting directly affected and the user won't be happy with the performance of the web application that they are interacting with. So going forward, where is the problem? Where is the current problem? AQM algorithms have been already discussed since, as Fred said, it all started from 1984, 1990, where people started talking about the queue management algorithms. But what happened and why have they become suddenly popular once again? So when I was doing my PhD work about 2008 or 9, there was not much interest in the community at that time on the queue management algorithms, because there was a lot of work that was already done on RED. And in 2010 is when it was not a problem that didn't exist earlier, but it just became worse and it became more prominent in 2011 when the word was coined as buffer bloat. So the word buffer bloat means there is excess of buffer, and that happened because the memory is inexpensive. So I was listening to Fred when he said that people were wondering at that time, can we have more memory? But at that time, memory was expensive. Now, since the memory has become inexpensive, what has happened is that the buffers at the routers have become bloated. They are really deep, very big. And if you tend to fill up those big buffers, you have an impact of very high queuing delay. And that essentially is the meaning of the word buffer bloat. So is it the case that before buffer bloat problem was identified, okay, I think there's some bit of noise.
I've muted everyone.
Okay, I'll try to mute myself and come back again. No, the problem doesn't seem to be from my side. I think yeah, okay. Is it better now?
It's perfect now. Go ahead.
Yeah, okay. So I think it was some issue. All right. So I hope my screen is visible, Dhruv.
Yes, it is.
Okay, thank you. So the problem of buffer bloat is not something that got identified in 2011. It's just that it became worse when one researcher at Alcatel-Lucent by name Jim Geddes identified that his home gateway was giving him a queuing delay of more than about 20 seconds. And that was pretty much surprising. We always have known this particular problem as persistently full buffers, but then the buffers were small, so the impact was not really big, even if the buffers were becoming full. The packets were getting dropped, but the queuing delays were still within control. The buffer bloat problem is the fact that you have a huge buffer and you tend to fill up. This whole initiative got started in 2010-11, and you can see this is the website in case you want to find more details about buffer bloat project. It's called bufferbloat.net. I've been doing a lot of work. Algorithm called Codal, which I'm going to discuss later in my slides, is also an outcome of this community where Van Jacobson and Kathleen Nichols worked with the buffer bloat community, Jim Geddes, Dave Tart, and got the things merged into the Linux kernel and then got them tested. So going further, there's another problem. So one is the problem from the network side that you have really deep buffers. Another problem is at the endpoint. So the problem is because of not just the endpoints or not just the network behavior, but it's a combined problem of both the entities. One, you have a big buffer, and on the other side, you have a TCP congestion control, which doesn't react to congestion until the congestion actually happens. And more importantly, the fact is, all the TCPs that we use currently in the operating systems like Linux, for example, Cubic is a popular TCP which is deployed in all the Linux operating systems. It's a loss-based TCP. As you can see in the diagram, there's a left arrow which says reactive loss-based TCP. Loss-based TCP means it will just continue to increase its sending rate until it doesn't identify a packet loss. And when you have a deep buffer, you need to fill up this entire buffer to get a packet loss. Otherwise, you're not going to have a packet loss, which means that this TCP is going to just keep overrunning the buffer, keep filling up this deep buffer, induce a very high queuing delay, and then ultimately get a packet loss only to realize that congestion has happened now. So this is quite a bit of a problem. And I think Kanan mentioned in the question to Fred about BBR. BBR actually attempted to do things otherwise, that they did not want to wait for a packet loss. And they wanted to react to congestion much before the buffers actually get filled up. And BBR is also an initiative by Google in a way to sort of avoid the buffer bloat problem, but from the endpoint side. So they try to do something at the endpoint so that the buffers don't fill up. But it has been known in the past that, while the efforts are very good at the endpoint, the best way you could control the buffer is by getting the network feedback itself. Let the devices in the network play an important role in controlling that buffer. And that's where this new topic comes in, which we call it as active queue management. And this has been a long game. People have tried doing congestion avoidance at the network side, as well as there has been an immense amount of effort on the endpoints to control congestion. As you can see, this chart, which I have borrowed from IEEE Communication and Service tutorial from 2010, shows that a lot of things have happened ever since RFC 793 rolled out with the basic TCP. And this is just information till 2010, even after which, a lot of new other TCPs have come. For instance, BBR is not mentioned in this chart because it's just rolled out a couple of years before. So these two are the main problem. One, you have TCP, which doesn't reduce its rate until a packet is lost, and other side, the buffers are big. So what happens when you take this entire scenario? This is a small diagram from an Australian journal paper, which is explaining the impact of buffer bloat on the IoT applications. Because in a home environment, you could have a mix of all the traffic. You could have a latency tolerant traffic, for example, heavy app downloads or operating system updates. And on the other side, you could have a latency sensitive traffic, which is an IoT traffic. So if you can see on the top, it says that you have a gateway which connects you to the internet. So what would happen on the link between the gateway and the internet, particularly when your traffic, such as your cloud-based applications or your office applications, file backups or file servers, all of this will collide with the traffic that's below, which is more or less an home automation traffic here. So you will have tiny time-sensitive traffic coexisting with throughput-sensitive traffic, and the requirements of both these traffics are different. You are perfectly fine if the file backups take a little longer, but then we are not okay if the IoT application doesn't respond within a few milliseconds. So both these traffics have completely diverse requirements, and the need is to somehow provide these two, to satisfy these two requirements by using some kind of queue management algorithms at the gateway. So I'll take things now into the potential solution that people have discussed. As I said, AQMs have been there since several years, even before the word buffer bloat was coined. But then people realized that these algorithms can well be used as solution for the buffer bloat. So it was just a new angle given to active queue management, and not that active queue management came into existence only after buffer bloat started. So that's not the case. And these algorithms are very popularly also known as queue disciplines in the Linux kernel. So if we go to the Linux kernel scheduler, we all call them as queue disciplines. So what Fred said, red is a queue discipline, WRED is a queue discipline, Pi is a queue discipline, and Codel is a queue discipline. So these algorithms have certain goals and challenges. Covering the goals first, their goal is very clear. They need to be proactive in the queue control to avoid congestion, not to wait until the queue becomes full and then drop the packets, and then the TCP understands that it needs to control its sending rate. No, we need to control the queue proactively, and hence, accordingly, we need to minimize the queue delay. But at the same time, while we do all of this, we should ensure that we do not affect the link utilization. So if I have a bandwidth of 10 megabits per second, I need to ensure that I need to keep that bandwidth completely occupied. Otherwise, I'd be doing resource underutilization. So I need to use my resources adequately, but I do not want to fill up the buffers. You can imagine this situation basically thinking of a water bottle, which I am holding upside down, and there's a bottleneck, which is downwards, and it is connected to a 10 megabits per second of bandwidth. And this bottle of water which I hold, suppose it can buffer up to 2 MB worth of packets. So if my input rate is 10 Mbps, my output rate is 10 Mbps, my link is completely utilized, but my queue is not filled up at all, and the delay is 0. Well, this is the ideal operating point, but we know that it's very difficult to have input rate control to match the output rate. At times, there will be input rate much higher than the output rate, and which is why we tend to start buffering in the bottle that I'm holding. So if I'm sending at 12 Mbps now input rate, 10 Mbps goes out, and the remaining 2 MB gets buffered. The logic here is, how can I keep my bandwidth completely utilized, but instead of buffering 2 MB, I buffer very little and ensure that the queuing delay is less. So that's the most important goal of the AQM algorithms, to operate at a point where your resources are utilized maximum and the delay is minimum. But what are the challenges? The challenges come when you have unresponsive traffic passing through the routers. What is an unresponsive traffic? The one that typically is congestion agnostic. For example, take a DNS traffic. DNS traffic is basically that's run something on UDP, and we don't have anything called congestion control over there. Or basically the ping messages, we do not have congestion control there. Of course, these are not long-lasting traffic, but when these kind of traffic comes, they tend to fill up the buffers. And even if you drop the packets of these traffic, they do not have anything called reduction in the sending rate. And that's something that affects the behavior of the queue a lot. So if you have a bunch of unresponsive traffic that is coexisting with the TCP traffic, TCP will try to back off because it's getting the packet drop signals from the queue management algorithm, and it reduces the sending rate. But the UDP flows wouldn't do that. And ultimately, it could lead to the buffer filling up. So it loses the purpose of having an AQM algorithm. The first thing of having AQM algorithm was to minimize the queue delay, have a good control, but then you are losing the queue control because there is a traffic that's not congestion aware, and it just tends to keep continuing the rate at which it is sending. Another problem, even if we don't consider the unresponsive traffic, and if we just consider the TCP traffic, we have most of the traffic that we see today on the internet is quite a low volume traffic. For example, search queries or small posts that we put up on Twitter or Facebook. And basically this traffic comes in a burst, it's short-lived, and its volume is very low. So what happens is, because of this burst nature, the queue sort of acts like a smoothing factor. So you have an input rate which is suddenly increasing to a very high level, and then you need to rely on these buffers to avoid dropping these packets. Because if you drop the packets of these tiny flows, then they are going to have to retransmit. And that's going to affect the overall application performance, because the latency will be even more, because you drop the packet, timeout has to occur, and then these packets have to be retransmitted. So the problem with the AQM algorithms is that they need to differentiate very beautifully between what is a temporary burst and don't allow that packets to be dropped. At the same time, find out whether it's a temporary burst or it's a persistent congestion. And if it's a persistent congestion, then you need to start telling the flows to reduce their rate. At the same time, do not impact the temporary burst that's passing by, because if you tend to affect this temporary burst, it's basically going to make the application performance worse, because you're dropping the packets of flows which are very tiny and are time sensitive. So with these goals and challenges in mind, I'll go ahead with the first algorithm for discussion today, which is called control delay. In short, we call it as CODEL. It has been described in detail in RFC 8289. And this algorithm, when it was released, it came and mentioned that, for example, RED algorithm, which was mentioned by Fred, it uses queue length as a metric. So you keep monitoring the queue length, and then you take an action whether you want to drop the packet or not. But Van Jacobson and Kathleen came and said that instead of using queue length, let's use queue delay, because that's something that the user perceives directly. And they said, okay, let's use queue delay as a metric for queue management. And they have two phases in their algorithm, a dropping phase and a non-dropping phase. When the algorithm is in the dropping phase, they drop the packets. In the other one, they don't drop the packets, and the algorithm starts with the non-dropping phase. And there are two configurable parameters. One is called the target queue delay, means I'm okay to buffer up to some amount of packets, which account for 5 milliseconds of latency, but not more than that. So you can read that target as target queue delay. And there's an interval, which I will explain later, which they have set it as 100 milliseconds. So I'll explain the functionality of the interval in a moment. So what they do is, when every time the functionality is like this, when the packet is going out, it's being dequeued. At that time, they try to find out how much was the queue delay that this packet had to actually face. And how do they do it is, whenever a packet is coming in the queue, they attach a timestamp, and whenever it's going out, they look at the DQ time minus the NQ time, and they get exact amount of time that this packet waited inside the queue. And what they do is, okay, so they say that this is the current queue delay faced by this packet, and then they do a comparison. Was it more than 5 milliseconds of target that I had? And is it the first time that I'm seeing this queue delay go more than 5 milliseconds? If yes, then they don't enter the dropping phase, but instead they start the timer, which is called interval. Now this is a catch. Why do not they immediately start dropping the packet when the queue delay has gone more than 5 milliseconds? Is because of the point that I mentioned in my previous slide, that they need to identify whether this is a temporary burst or whether it's a persistent congestion. So they do not immediately start dropping the packet if the queue delay becomes more than target. Instead, they wait for 100 milliseconds and keep monitoring. During this 100 millisecond, if they find that every packet that was departed had a queue delay more than the target, then it is a sign that this is a persistent congestion, because the queue delay is not reducing below the target and it's always consistently above the target. And in such a case, they would take a decision to enter into the dropping phase. So that's the point which I've written. They enter the dropping phase only if they identify that the queue delay is greater than target for the entire 100 milliseconds of interval. Suppose before 100 milliseconds could expire, they got a packet whose queue delay was less than the target, then they will conclude that it was not a persistent congestion, but rather it was a short burst, and they would just continue to stay in the non-dropping phase and they would not drop the packet. They would reset the interval, and then they will wait again for the queue delay to go more than the target. And again, when queue delay goes more than target, they will start the interval, start the observation period of 100 milliseconds. If they see continuous delay more than target, they go into the dropping phase. Now, what do they do when they enter into the dropping phase? So when they enter the dropping phase, the first thing they do is they drop this packet which was going out, and they maintain a variable called count to always remember how many packets have they dropped in this dropping phase. So since the count was 0 and this is the first packet they drop, they increment count to 1. What do they do with the next packet? They don't drop it immediately, because if they would start dropping every packet that's coming in, then you are going to impact the TCP throughput in a very bad way, and you will have underutilization of the link. So you don't want to drop every packet. You want to drop packets in such a way that you leave enough room for the TCP flow to respond. So if I drop a packet now, I would rather want to wait for some time and see whether the TCP flow reduces the sending rate or not. And if not, then I would drop again. Hence, Codal introduces something called control law, which is written in the equation number 2, in which they identify when to drop the next packet. So I dropped a packet just now, and that is my current time. When should I drop my next packet? The next packet should be dropped based on this equation, where you can see there is interval divided by square root of count. Now, interval is 100 milliseconds. We know that. And count variable has just become 1 because I dropped one packet. Square root of 1 is 1, and 100 divided by 1 means I dropped the first packet, and I'm going to wait for 100 milliseconds to drop the next packet. I'll drop the next packet. Next time, my count will become 2, and it will become square root of 2. It will not be 100 milliseconds. It will be lesser than 100 milliseconds. So what is the behavior that this control law gives you is that if you see that the sender is not responding to your packet drops, you will start dropping the packets more frequently. Initially, you waited for 100 milliseconds, then lesser than that, then even lesser than that, and the time would probably come that you would be starting to drop almost every other packet because the sender is not responding to your packet drop information. It's not reducing the sending rate. And that's why this control law has been made in this way. So while in the dropping phase, as I said, it continues to use this control law. But at any point, if the queue delay goes less than target, then this algorithm comes out of the dropping phase. Even if one packet faces a queue delay lesser than the target, it means that the queue has drained out, and now there are not enough packets in the queue, and that's the reason this particular packet faced less queue delay. So it's good time to go out of the dropping phase. When it goes out of the dropping phase, it resets the count value to 0, which is important to remember for my next slide, which I'm going to talk. It resets the count to 0, and it enters the non-dropping phase. It will come back to the dropping phase, again, based on the conditions which I said in the previous slide. So let us see what are the problems that are already known with Codal. The problem with Codal is that it's always anticipating that the sender is a TCP sender, because it drops one packet and waits for some time before dropping another packet. And if it's a UDP sender who will not be reducing the sending rate, the time that the Codal waits for dropping the next packet is sufficient amount of time for the UDP flow to actually fill up the entire buffer. So we did a small experiment, as you can see in the results. You can see the purple line is a codal, wherein you can see the description of this scenario is that we have 5 TCP flows and we have just one UDP flow. And on the left side graph, the queue capacity is 200 packets. And you can see that codal is not having a queue control. It's completely keeping the queue full to 200 packets. It's taking time to become aggressive enough to drop the packet. And then again, it comes back to 200 after a while. So it tries to control the queue being aggressive. As soon as the queue delay goes below target, it goes out of the dropping phase. Again, the queue builds up and this cycle repeats. We wanted to check whether this will be the same behavior when we increase the queue capacity to 10,000 packets, and that's the right side plot. We increase the queue capacity to 10,000 and you could see the codal repeating the same behavior. It goes and fills up the entire buffer and comes back trying to control it. The moment it thinks it has control, it goes out of the dropping phase and then it again fills up the whole thing. Let me tell you one thing. If I remove this one UDP flow, which is, you can see the description of that scenario in the paper, which we have written. I have given a citation to it in the bottom. If you could just remove this one UDP flow from here and just keep TCP, you would see codal working perfectly fine. It controls the queue within 5 milliseconds and without affecting any queue utilization. The only problem is because there is an unresponsive flow and the control law of codal is just permitting it to fill up the buffer all over. So this problem has been solved in the kernel right now. We have codal also in the Linux kernel. There's something called FQ codal, about which Fred mentioned in his last slide, which is basically a flow queue codal, and it tries to provide a kind of a separate queue to the incoming flows so that one flow does not affect the performance of the another flow. You isolate a UDP flow from the TCP flow so that if UDP is pumping a lot of traffic, it's just in its own queue and not in the TCP queue. So TCP doesn't have any problem. You might lose the control on the UDP queue and it might fill up the UDP queue, but you still tend to give better performance to TCP flows, particularly because they are responsive. So this is one of the problem and the solution. The problem is unresponsive flows cause problem. FQ codal sorts of tries to solve that problem. Now, how do they identify the flow? I'll not go into more detail, but I have just written a high level of overview here that an incoming flow is identified by using 5 tuples, which is the source and the destination IP address, source and the destination port number, the protocol number, and using these 5 tuples, they apply in Linux kernel Jenkins hash, and you hash it into separate buckets. And they have, as of now, they have about 1,024 queues which are available, and up to so many flows can be classified. There is a probability of a hash collision there where you can have multiple flows getting hashed onto the same queue, but then, well, that's not the focus right now in the talk. And there are more details in the FQ codal RFC that they provide. In fact, there are many other hashing mechanisms being researched at IETF to actually minimize this hashing collision chances. So, second problem, as I said, in my previous slide, I said they reset the value of count to 0, and this is the problem. Look at a situation where they come out of the dropping phase and reset the count to 0, and immediately the queue starts filling up once again, which is exactly what's happening in our plot. So what happens is you lose all the heuristics that you had obtained from the dropping phase. You increase the count to a very high value. Maybe you dropped 1,000 packets, your count was 1,000, but the moment you came out of the dropping phase, you just reset it to 0. You forgot what you did in the previous dropping phase. What was the intensity of congestion in the previous dropping phase is completely lost, just because one packet's queue delay came lesser than target. So they tend to lose this information, and to enter into the dropping phase, they wait again for 100 milliseconds, and they follow the same control law. And you need to get that information once again. And for you to become very aggressive as a codal algorithm, you need to go through the entire cycle again and again, which clearly is something that you can see in my plot. It becomes aggressive and tries to control the queue delay, so purple line comes down, but it loses the control immediately afterwards because it thinks now congestion is not there and just keeps repeating. Well, there is something that I have not explained in these plots, is that you see an algorithm called Cobalt, which is in green line in the plots. This is an algorithm which is called Codal Blue Alternate. That's a full form of Cobalt. And it was made by Jonathan Morton, who is also the co-author with us in the paper that we have written. It's a slightly different version of Codal, and it tries to solve these two problems. But you can see that problem is not completely resolved, because even Cobalt at least for first time goes and fills up the queue at 200, or even on the right side, you can see it fills up the queue up to 1000. But yes, it does improvement over the Codal in the sense that henceforth it is able to control the delay. And Jonathan is still working on this problem, and he has recently written some new drafts in the IETF TSVWG group, where he is trying to tackle this initial problem of Cobalt, where it goes and fills up the queue completely. So this was a brief, very brief about Codal, and I'll go over quickly the Pi, which is the next algorithm. It does something similar. It also uses queue delay as a metric for queue management, but it doesn't have something called dropping phase, non-dropping phase. Instead, it always tries to calculate a drop probability. And based on this drop probability, it will decide whether it should allow the packet to be enqueued or it should be dropped. So Codal was operating at the DQ time. Pi typically operates at the NQ time. So when a packet comes, you take a decision whether you want to allow this packet to enter the queue. Whereas in the Codal, you take the decision at the DQ time. So like we had a target in Codal, 5 milliseconds, there is the same target here in Pi, but the RFC chooses it to be 15 milliseconds. And this is also called in RFC as reference queue delay. So it has two names. How does it work? It basically is an enhancement. As you can see in the name itself, it says it's an enhanced version of the PI controller. So PI controller is another AQM which was proposed sometime around 2000, early 2000. And that used to take queue length as a metric. This one takes queue delay as a metric. And the equation number 3 tells how the drop probability is calculated. So you always calculate this drop probability at an interval of 15 milliseconds, as I have written in the first bullet of functionality phase. And it's called T update in the RFC. So what you do is you keep calculating this probability every 15 milliseconds. And what do? You try to identify what is the current delay, what is the expected delay. Expected is the target one. How much away I am from the expected delay. The second part of the equation looks into where I am right now, where I was before. So old queue delay indicates where you were before in the previous sample and where you are in the current sample. So you get to know the trend. Trend means whether your queue delay is increasing or it is decreasing. And that is indicated by the second part. The first part tells you how far you are away from the target that you have in your mind, which is also 15 milliseconds. And you can see that they are multiplied with the constants A and B, which we popularly know that they are PI control parameters that control the actual drop probability. Using this drop probability, what they do is they generate a random number called R, and they compare the drop probability with a random number. So if the drop probability that you have right now is larger than R, then basically the packet is dropped because it's indicating that higher drop probability. And if the drop probability is less than R, then you will enqueue it. The R has to be a uniformly distributed random number, and it has to be between 0 and 1 since it's compared to the drop probability here. So you look at the drop probability all the time for every packet and compare with R, and then you see whether you need to enqueue the packet or drop the packet. Now let's go into the calculations. We spoke about Codal, and we know how Codal calculates queue delay, but Pi does it in two ways. The second one you can see is the same like Codal, but the first one is interesting. The first one is called Little's law, equation number 4. And equation number 1 is repeated from the previous slide, hence it's equation number 1 here as well. So you can see they say that you can estimate the current delay by looking at what is the current queue length and having a notion of what is your average departure rate. So if I know I am departing the packets, if the channel has been accepting my packets at a rate of say 9 Mbps, I know that if my current queue is having 50 packets and if my departure rate has been 9 Mbps, I can develop a notion of how much time will these 50 packets take to go out and what is the queue delay at this point of time. So it's an estimate of a queue delay by using the queue length, which is directly extractable from the queue, and you have an estimate of yours by using the average departure rate. So that's again an averaging equation which is provided in the RFC. For more details, you can see there, but a high-level overview is that you just have a notion of how much is your departure rate, and you keep an idea. Okay, my departure rate is so much. I have these many packets in the queue. They will take total of this much amount of time to go out. So this is my queue delay. Second thing, as I said, like Codal, you could do a simple calculation of queue delay, which is just the DQ time minus NQ time by using timestamps. And I want to talk more about these two estimations of current queue delay in the next slide. And I have omitted some of the features that Pi has because Pi is a pretty big algorithm with lots of enhancements done beautifully. And you can see I have just summarized them quickly here in the other notable features in RFC 8033, which is the official RFC of Pi, in which they also take care about the burst allowance. Burst allowance means you allow the small burst to pass by, like Codel was allowing small burst to pass by. Pi also has that feature. Pi auto-tunes the drop probability. For example, if the queue is building up very quickly, you don't want the drop probability to rise very sharply, otherwise it will drop a lot of packets in that process. So they put a cap that drop probability can increment only in steps, not a sudden increase, so that you can avoid the packet drops in large numbers. At the same time, when the queue becomes idle, you want to decay the drop probability, because if the queue is idle and a packet comes, just because it finds the drop probability to be high, it shouldn't be dropped because the queue is idle. So you don't want to drop an incoming packet when your entire queue is idle. So it has a feature called decaying the drop probability. And it also has a feature that you need to activate Pi only when certain amount of packets are there in the queue. If your queue is completely empty, then you don't want to basically use Pi, because you need to do probability calculations, you need to do queue delay calculations, you need to do average departure rate estimations. In short, you need to do a lot of calculations for running Pi, and you don't want to do that if the queue length is not sufficient enough. So if the queue length is beyond a certain threshold, RFC mentions that we can activate Pi, and if the queue is below that threshold, we can deactivate Pi. I'll just leave with this brief right now, with a hope that I want to talk more about the queue delay estimation, where we eventually found out the problems. Before I go to identify the problem, I'll just put a question here. Where do AQM algorithms actually operate? So this is a small diagram which I found out from an article called Queuing in the Linux Network Stack, and I use it in my classrooms to teach to my students. So basically, you can see in this diagram, on the right side is a NIC, which has its driver queue, which has the packet descriptors, and you have the actual queue discipline, which is indicated by number 2. So number 1 is a driver queue, which comes along with the NIC, and we don't run any queue discipline over there. It's just basic FIFO. Whatever I discussed here and whatever Fred said, read, and stuff like Pi and Codel, all of them, they run at 2. That is a queuing discipline. So how does it work? When the packets come and the driver queue is filled up, which I have written in the bullet at the top, when the driver queue becomes full, it doesn't drop the packet. It sends a stop signal to the queue discipline. And queue discipline will stop dequeuing the packets and sending them to the driver queue. It will wait. So what happens now? Driver queue is full. It's telling the queue discipline to stop. Queue discipline has stopped sending the packets, and hence the buffer starts becoming full at queue discipline. The packets start getting buffered there. After a while, you can see I have highlighted in the red color, when the driver queue has some space. I'll talk about this some space in a while. So when the driver queue has some space, it sends a wake up signal to queuing discipline. And then queuing discipline starts sending the packets again to the driver queue. This is how basically things work. This is a typical operation in the Linux kernel stack. Now, where is the problem? The problem is because of this some space. I'll explain it in the next slide. So you can see this is the same diagram. I have just made it a little smaller. So if you remember, I have repeated that equation number 4 for a quick overview. We used to use Little's law. A quick recap here. Little's law is one way by which Pi calculates queue delay. So that is a default approach suggested in the RFC. So that was the one that was implemented in the kernel. But when my PhD student was doing an experiment, we found some strange behavior that when the bottleneck bandwidth was 10 megabits, average departure rate was estimating more than 10 megabits. And we couldn't understand why is it happening. So this is the reason it was happening, which we could identify at a later point. So you can see I have indicated a green color actual departure rate. So what Pi intends to calculate in its average departure rate equation number 4 is the departure rate from the NIC to the channel. But unfortunately, what happens is it ends up estimating the departure rate, which is indicated as spurious departure rate. Now, why does that happen? When the driver queue is full, it sends the stop signal. But what is important, when does it send the wake up signal? It doesn't send the wake up signal when there is room for one packet in driver queue. It doesn't do that. And that is why in the previous slide, I said some space. So depending on which company's adapter we use, suppose I'm going to show you the results with the Intel adapter and the Broadcom adapter. You can see that in those results I'll show you, they do not send the wake up signal when they have one space in driver queue. most of them, they wait for some amount of space to get created, and that sum depends on the manufacturer. It could be different for an Intel card versus a Broadcom card. So what happens ultimately, the queue discipline is waiting for a wake-up call, and when the wake-up call comes, the driver queue has some space, and queue disciplines send the packets, they dequeue the packets in a quick burst, and they go and fill up the driver queue once again. So Pi ends up estimating the rate at what packets are actually going from queue discipline to driver queue, and thinks that my departure rate is great. But actually that departure rate is from queue discipline to driver queue and not from queue discipline onto the channel from the NIC. So this spurious departure rate estimation was affecting the entire calculation of current queue delay. And we could see that Pi was not able to control the queue as expected. I'll show the results in the next slide. So what did we try was a simple solution. Thanks to RFC 8033 once again, they mentioned that option in their RFC, that an alternative approach is to use timestamps like Codel does, which I have mentioned in my PPT. So a simple solution that we implemented in the kernel was we used timestamps to calculate queue delay, and we avoided Little's law. In fact, this patch is also now merged into the kernel, where timestamps is the default approach now to calculate queue delay in Pi, and the second one has been made optional in case people want to do more research about it. But this is a slide where we explain the paper. The paper is cited below, but just a quick overview of the results that we have here. In this one, you can see that there are two adapters that we have used. We have used Intel adapter E1000E, and we have used Broadcom adapter TG3, and we use different TX ring size. TX ring size is basically the device buffer size. And we can see the expected backlog, as I have written on the right side, the expected backlog in the sense the amount of data that should be in the queue to control queue delay should not be more than, should be around 180 KB. A little bit up and down is okay, but around that time. But you can see these are plots that are telling you the center line that you see in the box plot is the median, and the other one is the 75th percentile and the 25th percentile. And you can see that in E1000E, basically you can see the queue log, queue disk backlog is very high, around 800 KB, and with the Broadcom is also very high, about 400 KB, and on the left hand side with 256, you can see it's more than 600 KB. This is with the Little's law approach, in which we were seeing the problems in average departure rate. The below one is the one which we use timestamps, and you can see there that all four of them, all four cases in this particular example, are around that 180 KB, which is the expected behavior from Pi, depending on the straightforward calculations of the queue delay. So we have summarized more things about it. This is just a brief, these are just brief results. More detailed results are available in the Computer Networks journal paper, which just came online 10 days back on 22nd April. So this is something that we fixed. And finally, touching upon the FQPi, which is a variant similar, which is similar to Codel, but except that FQ Codel makes different queues and runs Codel on each queue. Like Fred said, you have multiple queues and each queue running red, and each queue given a different weighted red. What we do here is we have different queues, and each queue runs Pi instead of Codel. So we implemented this particular approach, and we have kept timestamp as the default in FQPi also, and we were able to get it accepted in Linux, and our code got released in 5.6, just March 2020. And the details about that implementation are also provided in the paper below. I just want to add one more point and then go to the conclusions, is that when we were doing this particular experiments and we were facing the problem of the spurious departure rate and actual departure rate, this problem did not manifest when I was using simulators like NS3. The reason was very simple. In NS3 also we have a same structure, which is mimicking the Linux kernels exactly. The only thing is, in NS3, the driver queue, whenever it has even one packet worth of space, it sends a wake-up call to the queue discipline. So the problem of calculating spurious departure rate was actually not manifesting in NS3 or any simulator. But the reason was very simple. The driver queue was sending a wake-up signal immediately as soon as it had space for one queue. The problem that happens in the actual systems is because the driver queue doesn't send a wake-up signal when it has just one packet space. It just waits for like 3 or 4 packets or even more sometimes and then sends it. which ultimately leads to a burst coming out from queuing discipline and entering into the driver queue, and hence giving us the spurious departure rate. That was just one point that I wanted to add. These are some primary experiments that we did with FQPy in our paper. We wanted to show that TCP cubic and BBR from Google, it was at that time when we were writing this paper, there was already a lot of evaluations in the conference papers and journal papers showing that BBR is unfair with cubic. And we also observed the same behavior on the left-hand side, where you can see the cubic flows, which is indicated by a slight shade of blue and green. They are all below. And the BBR 01 and 02 flows are just taking away all the throughput. And what we show by using FQPy is that because you have a flow isolation, you can see that cubic flows are not getting punished, and there is a fairness among the throughput that is achieved by all the flows. But yes, of course, more deeper investigations are needed, and we are still continuing to work on BBR, and Google has released a new version of BBR, which is called BBR v2. So we are looking also at that front, at how good it can solve the buffer bloat problem at the endpoint, and whether they need any support from the AQM side in the network or not. Coming to the end of these slides, I would just like to mention two tools which I find myself very easy to work with for quickly getting accustomed with this area of queue management is Flent. It's called Flexible Network Tester. It's a Python wrapper around netperf, iperf, and the well-known Linux tools, so that you can extract nice looking plots and you can configure different TCPs, and it provides a very good number of pre-configured tests. So for example, the results which I showed here of BBR versus cubic, this test configuration was already available in Flent, and all that we had to do was just enable Pi and then enable FQPy. It was really super easy for us to use Flent and extract the results of good quality and showing the right kind of results that we wanted to show in the paper. Another thing that we have done at NITK with the help of my students is that we have followed RFC 7928, which is RFC, informational RFC, which tells about different kind of benchmark scenarios in which we should evaluate AQM algorithms. And there were quite a lot of scenarios mentioned in RFC 7928. So what we did at NITK is that we have developed an automated framework in NS3, wherein you can just come and run one command. And NS3 has at the point of time right now about 8 or 9 different AQM algorithms. It will take these 8 or 9 algorithms and it would run against all the scenarios of RFC 7928 and generate maybe hundreds of plots in about 3 hours of time. And the researchers could just go and look at those plots and could rerun them again. And we have lots of other features provided in the tool, such as if you don't want to evaluate some algorithms, you could choose to ignore them in the evaluation. Or if you are adding a new algorithm of yourself, you could use your own algorithm inside this tool. So we have made it openly available since a couple of years. People have been using it and we keep getting feedback and improving it. It is called AQM Evaluation Suite for NS3, and the details are available on the website here, including the paper that we published in Workshop on NS3 on this part. So I think that is pretty much what I wanted to talk about. Thank you very much again for giving me an opportunity to be a part of the RFCs we love. It was a pleasure.
Thank you, Mohit. Thank you. It was a really great presentation. Thanks for explaining this, which even us folks who are not in the domain could follow. So thank you for that. Any quick questions from folks for both Fred and Mohit? We are running a little bit late, so keep it brief. If you have a question, please go ahead. Anybody has any questions? I have. By the time we are waiting for other people, Mohit, did you ever thought of applying for ANRP? This is a IRTF things that where they do applied network research prize for the papers related to ITF work usually. So if you are not aware of it, maybe I'll send you some details of this offline. And I think like the couple of papers that you are mentioning would fit in very well. And then you might have an opportunity even to present this during the ITF meeting as well. So I would suggest you to look into it.
Yeah, sure. Thank you very much. That will be nice. And is it something related to the applied networking research workshop that they conduct?
Yes.
Okay. Okay. Yeah, I just got to know about it, and we have submitted a paper for the Madrid ANRW. but I was not aware that we could put these papers there. But yeah, thanks. Please send me the link. I'll go into more details and check there.
Hey, one common question, like, is there any specific thing for the very low latency? Because here we are talking about generic thing, right? Like, we know that currently the ultra low latency is becoming the a lot of network, like a tactile internet and all those things we are building. Is there any specific works going on to reduce the low latency kind of networks?
Yes. So in this, in this recent IETF, which is virtual, I attended the TSVWG's discussion. It was mainly about talking L4S, which is called low latency, low loss, scalable throughput. That's the full form of L4S. Okay. And a lot of industries are showing interest towards L4S, which is kind of designed. It provides you a double AQM. It's called dual queue coupled AQM. That's the exact name which they use. And it tends to provide an ultra low latency. And a lot of companies in related to 3GPP work have been taking it forward. And we heard that some of them have even gone and deployed it for testing purposes.
Okay. Thank you. Thanks, Mo.
Right. Okay. Thank you.
Thank you, everyone. So let's move to the next topic. Next, we have current state of DNS and DOE, which is DNS over HTTPS. And this will be done by Swapneel Patnekar from Shrestha IT Technologies. He's a network engineer and researcher with interest in DNS, DNSSEC, BGP, security, Unix, etc. He is also an APNIC community trainer, a RIPE Atlas ambassador. So let's welcome Swapneel.
Thanks, Dhruv. Am I audible?
Yes. Swapneel, would you like to share
yes.
your screen?
Yes. Just before I do that, how are we doing on time?
So we are running 10 minutes late. I originally planned your talk for 45 minutes. So maybe if you can try to cover in 35 to 40, okay, including questions.
Okay, I will do that. Just sharing my screen. Can you guys see this?
Not yet. Yeah, it's coming. I think you can start.
Okay, great. All right. So just a little bit about me. More specifically, before I go more in detail on this specific slide, a little bit of heads up. I am more used to the 3-day or the 5-day workshops that I do. So this is a very interesting experiment to present a topic like DOE virtually. So any kind of feedback with regards to anything constructive, bricks, bats, buckets, please send it my way. So this is the brief outline that I will be perhaps trying to cover in this presentation by going with the traditional state of DNS, what we currently have. And before going into more detail about why, into the nitty-gritties of the protocol itself, I would probably go about doing it a little more differently and talking about why DOE as a DNS over HTTPS matters for that matter, or why the protocol or why the RFC came into existence. Then move on to going into the semantics of the protocol. Then I will also try to bring a different perspective about from the user end, as well as the CDN perspective and the network operators perspective, and also talk about implications of DOE from a corporate network angle as well. Then the current state of DOE, and probably take some questions if you have any. So this is this is not the entire DNS delegation chain for that matter, but this is the part of it which probably is very relevant to the topic at hand, which is DOE, right? So you have something called as stub resolvers, which are basically part of the operating system. And then you have something called as recursive resolvers, which may also be acting as caching or forwarding resolvers, which are finding the answer by going down the delegation chain and giving the answer back to the stub resolver, which is then used by the application layers for that matter. So one of the few problems which the community, the IETF community, has been trying to solve from a DNS perspective is for the point from the point from the beginning of DNS, the protocol hasn't been secure, so it is primarily encrypted. So the entire communication between the stub resolver and the recursive resolver, for that matter, is completely encrypted. And here, a point to be noted is that I have primarily specified this as DO53, which means DNS over port 53. That is a traditional DNS what we are currently using, except for maybe parts of the US where, let's say, Mozilla Firefox is by default, has a trial running where DO is currently is in use. So the queries and responses primarily travel directly over UDP and sometimes even on TCP. So a few problems with respect to DNS which exists at this point of time is it can be easily intercepted because it is unencrypted. It can be because it can be intercepted, it can be blocked. It can be also redirected and even modified. So a couple of use cases from that perspective is in regimes where there is censorship in place, you would see that DNS is being or has been used for redirection or blocking, access to websites entirely. Another security aspect of DNS or a loophole with respect to the current DNS what we have is, as it uses UDP as the transport layer, it has a huge attack surface with respect to DNS amplification attacks, for that matter. So I also do a lot of internet measurements using the RIPE Atlas. And one of the recent things which, apart from the RIPE Atlas, I have seen is there are roughly not less than 60,000 to 70,000 open resolvers in India at this point of time. So these are basically, bad configurations, or maybe there is a faulty bug in the software, or the CPU devices have a resolver which is even accessible for everyone from the WAN side. Irrespective of that's a huge volume of open resolvers which can be used for something like an amplification attack. So this brings into the picture of why DNS over HTTPS. And before even I go into that, there has been considerable amount of effort from the IETF to plug some of these security issues as well as privacy issues. And I can probably point to a couple of RFCs, which might be relevant from this perspective. Is one of the RFCs which is probably a precursor to something like DO that I would suggest everyone to go with is the RFC 7626, which talks about DNS privacy considerations, and that is something that is very useful in context. So keeping in mind from DNS over TLS or DNS over HTTPS, for that matter. The other thing what the IETF community has also done is has introduced an RFC which is 7816, which is DNS queue name minimization, that is query name minimization. So what it apparently does is, so the queries which are being sent by the recursive are the full queries which are going to the entire delegation chain, even though most of the name servers might not have a authoritative answer to it, right? So the query name minimization basically minimizes what part of the answer is expected from that name server, for that matter. So you can also look into RFC 7816. The other thing what has happened before from a historical perspective, before DNS or HTTPS or DO, which I will be talking about, is RFC 7858, which is DNS over TLS, that is transport layer security. But I think one of the reasons why that probably did not take, did not have that much traction to what DOH has is probably a couple of reasons for that. And one of the reasons for that is the element of blocking the endpoint for DOT, right? So DOT primarily uses port 853, which can be easily blocked at the network layer. So RFC 8484. So what it tries to primarily do, and most of the material on the internet, or most of the presentations or whatever I've seen so far, are only talking from a perspective of user privacy and security. But based on the reading of the RFC, it is also clear that there is also a performance element to it, which the specification is trying to from an implementation point of view. It's basically getting DNS into the HTTP ecosystem, right? So the problem with respect to DNS, as I mentioned in one of the earlier use cases, was on-path interference, where there is a on-path device, there is a middleware box which is perhaps intercepting DNS traffic and redirecting it or blocking it, which is commonly found in when we access public networks, let's say at the airport or at coffee shops, or somewhere some networks where we do not have a control over, right? So so that's the main intention of the specification. Apart from that, it also the intention is to have web applications or applications per se. I think I should make the change to refer it to applications, is to have access to DNS information, which was necessarily only available by sending the request to the operating system, and then the stub resolver would send it to the network, that is a recursive DNS resolver. So I think this is a very important point to be considered when you're talking about DOH for that matter, because the whole idea is not only from a privacy perspective, it is also to bring DNS into the HTTP ecosystem for that matter. So the authors of DOH are Paul Hoffman and Patrick McManus, and the idea behind this is that DNS queries and responses are over an encrypted transport. So at the last mile, so if you look at back to the previous diagrammatic representation, the communication between the stub resolvers and the recursive, that's the communication which is susceptible to abuse, and that's what this protocol or specification aims to do. So queries and responses are typically encapsulated inside HTTPS. And one of the advantages of doing this is DNS traffic when DOH is implemented. So DNS traffic, when it is inside HTTPS, it is mixing with other HTTPS traffics or other protocols, other protocols which are using HTTPS as a transport for that matter. So it becomes extremely difficult, or it becomes impossible to kind of modify or intercept for that matter, and that's especially going to be true with TLS 1.3. So an encrypted client stub resolver communication So the RFC also says that the DNS over TCP connections is the recommended minimum recommended is HTTP 2. It retains the same functionalities of the traditional DNS, which is the query response over UDP, what we currently see. The advantage, as I said, is apart from the privacy angle, is also the integration of being in the HTTP ecosystem of getting those added benefits for that matter. Some of them which I will cover in the next slide. So instead of using the DNS:URI prefix, which is the previous norm, it uses a URI path. So /DNS-query is something that is used. The HTTP2 protocol also provides reordering, parallelism, priority, and header compression. Some of the advantages of that specific protocol, which I will not go into currently, but that is something that gets that becomes an added benefit from a DNS perspective. So there are two elements here. So one is something called as a DOH client, and the other is a DOH server. The server is basically the endpoint where the clients would connect to, and that's where the encrypted communication would happen. But at this point of time, one of the problems with this from an implementation standpoint of view has been that there is no automatic discovery of the DOH server for the DOH client, for that matter. So it's currently a manual process where the unified resource identifier templates have to be configured manually into the DOH client, and that is something that you can also see if you access Mozilla Firefox, say for example, and if you want to enable DOH currently here in India, let's say, then you'll have to explicitly and you use your own DOH server. Even though the DOH server might be in your network, you'll have to explicitly set the URI template path. The DOH servers can support multiple URI templates. So there can be a possibility where for various service level agreements or for various implementations of what it does at the endpoint, there could be multiple URI templates there. There is a mention about a probable mention about pushing the URI templates, that is RFC 6570 via DHCP, but that is something that is currently not available as an implementation. The DOH server must implement the get and post methods for that matter. Talking a little bit more about on the semantic front from how this works is the DOH client basically when it sends a DNS query, it is basically encoded into an HTTP request, which is using either an HTTP get or a post. So in the case of the get method, the DNS query is encoded in base 64. The get method is obviously more friendlier with respect to HTTP cache implementations. The post method has to be in case of utilization of the cache, the client has to explicitly pass the header parameters, and in the case of the post method, the DNS query is sent as the message body. From a payload perspective, it retains the existing UDP wire format, or which is mentioned in the initial references with respect to the RFC 1034 to 1035 to begin with. It uses a MIME data type of application/DNS message, where previously this was in the case of DNS, when using UDP, that's limited to 512 bytes. But in the case of the DOH implementation or DOH specification, the size would be restricted to 65,535. So there is the other implementation which is also available, that is your DNS over JSON, that is JavaScript object notation. So payload is formatted typically using JSON encoding for that matter, and the MIME type is application/DNS plus JSON. In the case of the the DOH server, it must return a response for all DOH queries for that matter, irrespective, and this is true irrespective of whether the DNS response, which is inside the payload, even if the response to that was a non-existing domain, an NX domain, or it was a serve fail that it could not resolve it. So the response that comes back will be a response code of 200, say, for example. Here are a few error responses codes that I explicitly put out here, so that it is quite evident that it is using the HTTP error response codes which are available in that protocol, and there is no DNS element to it from a error code perspective. I am not sure if you are able to see this the entire screenshot, because the size of it is quite limited. But here is so what I've tried to show you here is basically using the curl command line tool is to connect to the quad 9 DOH resolver, resolving for a domain name which is my domain, which is brainattic.in, and you will see that the response that comes back has a lot of parameters which are quite similar to what you would see when you would run a dig query or a drill query on a domain name, right? And some of them, as you can see, is recursion desired. The RD so these are basically flags which you typically send inside a DNS query. Whether you need DNSSEC checking disabled, so you see the CD is false in this case. Here is another curl command line output, which is basically connecting to the Google public resolver, which has a DOH implementation as well. And you see that what you are seeing here is basically more specifically formatted JavaScript DNS over JSON object for that matter. In the case of caches, DNS and HTTP both have their implementations of a cache. In the case of responses to post, as I mentioned earlier, they are not cacheable unless and until a specific response header fields are set, and certainly not advised as per the specification to use to use caching from using the post method. Certain implications that I'd like to mention now from implementations or the protocol perspective is, one of the implications from a corporate network perspective is there are a lot of corporate policies in place where DNS is monitored and even filtered for preventing malware, preventing for threat hunting for that matter, for blocking bad requests or even newly observed domains for that matter. And this implementation from a Dove perspective in the network brings its own set of challenges because that is something now is not possible, and it becomes more difficult from a security perspective for that matter. So as an example, I also set up a lot of DNS firewalls using DNS RPZ, that is response policy zones, and that is going to be more difficult in the DOH implementation unless and until the endpoint is something that you control. Another problem with respect to DOH, from an implementation perspective, of course, this is too early at this point, and there is a lot of the domain is quite rapidly moving. But one of the other problems with respect to DOH as a perspective, as an implementation at this point of time, is the split horizon DNS, and probably I'll explain this with a diagrammatic representation. So in the case of the split horizon DNS is, in the case of a corporate network, let's assume that there is a on-premise DNS server which you can see, which is inside the network, and it is protected by, let's say, a firewall. And there are users in the network which are typically accessing using this recursive or this authoritative DNS, and they get one set of query or one set of answer when they query, let's say, www.example.com, and they get the IP address as 192.168.1.1. But let's say there are external users who are also part of the corporate network, and when they access authoritative servers which are on the internet, and when they have the same domain name is being used, what is part of the private namespace in the corporate network, the answer would be, let's say, for example, different. So in this case, when DOH is being used, the existing DNS authoritative server is something that typically does not come in the picture, and that causes a problem. So currently, in the case of, as an example, if I look at what Mozilla Firefox does in handling split horizon DNSs, if you have a domain that is publicly resolvable, but it resolved differently internally, then you should use enterprise settings to disable DOH. So that is something that is a challenge at this point of time. And I believe there is a specific group of people who are working on the ADD mailing list, if I'm not mistaken, which are looking at solving this problem. The other perspective is the perspective of a CDN content delivery network provider. In this case, the content delivery network is basically using is basically answering to the requests depending on where the user is. by using something called as Anycast in the routing domain. So ideally, when I access, say for example, a resource, when my recursive resolver connects to the authoritative servers for the content delivery network, depending on my location, I would get a different response than what you would get from your location, say for example. And let me probably explain this with diagrammatic representation. So here you see users who are accessing at the last mile from different geographical locations. So this is primarily location-based DNS. So using IP Anycast, everyone gets a different answer depending on the location where they are. This causes a problem with respect to DOE at this point of time, primarily because when the user is now using a DOH resolver, the centralized DOH resolver is now sending its IP to the Anycast, name servers for that matter. So the response that the Anycast name servers would give would be depending on the location of the DOE resolver. So there might be, of course, there has been study which I'll point you to, but there has been, there is a potential to see if this causes a problem. And based on studies done so far, a couple of references which I'll point you to. One of them is done by Mozilla, but I think Chrome at this point of time has not enabled DOE, and that it's going to be super interesting to see what happens when Chrome enables DOH. Because from a market share perspective, I think Chrome has a market share of roughly more than 60% of it in comparison to what Mozilla Firefox does. So here is the example that I wanted to show you. So LOC DNS is basically a small script that I wrote yesterday to demonstrate this. So what it primarily does is and I'm running it from two different locations. So there are two images on this slide for that matter. One of them is from my laptop, and the other is from a DigitalOcean droplet or VPS for that matter. So in the first part, what it does is it shows you your IP address, and the second part it shows you what ASN what is your upstream provider's ASN for that matter, and the third is it is resolving google.com, and it is showing the IP. So in the first instance, I'm getting the IP as 216.58.203.206. And in the second instance is when I run LOC DNS, you see that my IP is obviously the IP of the droplet, and the ASN is 14061, which is the DigitalOcean ASN for that matter. And you see that Google resolves to 172.213. So it's a different. So based on the location, I'm getting a different response. So this is the current way in which DNS is utilized by content delivery networks, which could be impacted going forward. I think it's very important to also mention about the current state of DOE. So Google Chrome, I think, pushed back the release for I think it was, if I'm not mistaken, it was a 73 release, which they have pushed a little forward because of the COVID-19 situation. But I think it's going to come probably in a month or so. So you can check the link which I have put in the presentation slides to look at that. For the DOH resolver discovery problem, as I mentioned, as well as other problems, what are being addressed by the ITF community, there is a specific mailing list where these problems are being actively and rapidly being discussed. And so I suggest you look at the ADD, that is Applications Doing DNS mailing list. So there is an experimental tool on Android at this point of time to test DOH for that matter from a DOH client perspective. There is a list of public DOH resolvers which you can see. Of course, this is a user-generated list, so there might be a possibility that there are a lot of DOH implementations which are not currently there. Microsoft also has announced that DOH is going to be a part of the Windows operating system, so that's an excellent news going forward. A couple of other challenges are from a load testing or benchmarking perspective. There are lack of tools supporting DOE at this point of time, so there is a lot of work needed in that space. So the DOH, the other problem which I have also seen is the DOH client still has to resolve the DNS URI. So this is like a chicken and egg problem, right? So if I, let's say in my Firefox browser, if I put a DOH URI endpoint and it's a domain name, then that has to resolve first before even the encapsulation, even before the TLS kicks in. And that is a problem because traditionally networks can then block based on that. So current solution, what the specification mentions is to use IP-based URI, and that again has a problem to begin with, because there are a lot of CAs which do not allow certificates based on primarily an IP address basis. And I've seen cases where implementation is also an issue. I think Quad 9 has a centralized door resolver, as well as Quad 1 by Cloudflare. So that is the problem. So other solutions what are typically mentioned here are make initial resolution part of the configuration, and I think the ADD mailing list, there is a lot of work being done there as well. Going forward, I think the encrypted server name indication that is currently being worked on and is basically a draft at this point of time is going to address this going forward. So this is worthwhile to mention because I just cannot attribute this quote to somebody, but long time back I read this somewhere and it just struck me that DOH or even DOT for that matter only protects privacy if the DOS server is honest, right? And I mentioned this very specifically because one of the intentions of the protocol is to secure the client to sub-resolver to recursive resolver communication. And the whole point of this was also use cases where internet service providers or network operators for that matter hijacking DNS requests and blocking, censoring, showing ads, etc. But a surprising initiative by a lot of network operators has been is they are also doing a lot of DOH trials. So I probably chose 3 of the most prominent from a density of user perspective. So AT&T has a DOH trial for that matter, as well as Comcast and British Telecom as well. All of the COD resolvers typically have DOH implementations which are not production ready to begin with, but they are currently being tried, currently being tested. I think the COD 9 one is not as per the RFC 8484 specification, so you might want to maybe check on that. State of DNS server software. So bind support for DOH at this point of time in bind is probably expected by the end of 2020, and Mozilla basically awarded a grant to ISC bind to implement this. Power DNS, that is DNS dist, which is the front end, the load balancer DNS server software already has support for DOH for a very long time. The NOT resolver also has support for this. So if you're looking at implementing, that is something that you can see. So a couple of references that I would like to point out from a performance perspective, which I mentioned a few slides back, is there was a study which was done sometime back comparing the effects of DOH, DOT on web performance. And Mozilla, so there is a link to that paper, you can check that out. Mozilla also did a test, I think, a while back, primarily to look at the impacts on CDN, the results of which, as per the paper, were very, very promising. There wasn't much difference with respect to performance per se. But having said that, I think sample size would be very important in this case. I think this slide got duplicated. So I think I have pretty much covered most of the presentation, and thanks for having me. So I would be happy to take any questions if you have for that matter.
Thank you, Swapneel. Swapneel, one quick question. Where does DNSSEC fits into the whole this thing? Could you clarify that as well?
Sure, that's an excellent question. I think DNSSEC, for that matter, primarily looks at the. So if I have to put it this way, DOH and DOT are securing your channel of communication between the client, that is a stub resolver, and the recursive resolver. DNSSEC, on the other hand, is basically verifying the authenticity of the data, of the DNS data. So when you query, send a DNS query, and if your recursive DNS resolver is doing DNSSEC, and if the the domain that comes back, the response that comes back, if there is some let's say man-in-the-middle attack, your recursive resolver will not give you the answer. So protecting you from man-in-the-middle attacks, for that matter. I hope that answers your question.
Yeah, definitely. And also interesting thing that ADD working group, initially it was called Application Doing DNS, but later the name got changed to Adaptive DNS Discovery, keeping the thing ADD still, the working group name being still the ADD, but it's being called Adaptive DNS Discovery now.
Great. I need to update my slides. Thanks for that.
Any other question, folks?
Hi, this is Nemo. I had a question on the OS level support. You mentioned that Microsoft is building in support for DO in Windows. And to what degree is the support in Windows? And are there other operating systems following suit?
I think that's an interesting question. So I haven't looked into how Microsoft is going to implement this in the Windows operating system going forward. But I presume, based on what I have read little so far, I think this is going to be available in the network settings itself, inside the operating system itself. This is probably going to be very similar to what Google did in Android, I think 9 plus, where they have DOT support by default, where you can enable DOT from the user space itself, that is the user level settings itself. So I think that's going to be very similar. The other, to answer your second part of the question is, I think this is, from an implementation perspective, it's going to be also very challenging and interesting to see, because every application, it's just not necessarily just the operating system or just the browser. It could be any application doing DOH, right? So implementation wise, and the challenge is going to be, each could be using a different DOH server endpoint. Right? Hello?
Yeah, thank you, Swapneel. Any other questions? Okay, so let's move on. Thank you, Swapneel. Thanks for a very good presentation.
Thank you so much. Thanks for having me.
Swapneel, would you mind disconnecting the sharing? Yeah, you have done. Thank you. Perfect. So next, we have a web payments API. This is our last presentation. Thanks everyone for staying back. This is by Nemo, who is also called Abhay Rana from Razorpay. Nemo deals with tech and security things and is passionate about making internet faster and more secure. He runs his own public encrypted DNS service for fun, and that's a good hobby, I guess. And he's a self-hosting enthusiast. So let's welcome Nemo for our last presentation. Nemo, you can share.
I thought I'm already sharing. Does it show up?
Yeah, it's showing. Go ahead.
Okay. It's still showing up, right?
Yeah, it's showing.
So hi, I'm Nemo. I do tech and security things at Razorpay. I'm going to be talking about web payment APIs. And this is not an IETF standard or anywhere related to IETF in general, but I believe it's a standard that we should all be looking out for in terms of how the payments ecosystem is building out, especially with how it's doing in India. I'm Nemo. I do tech and security things at Razorpay. I deal with infrastructure, security, I deal with compliance a bit, and a host of other things. Which is why payments. Razorpay is a payments processor and a payments application layer for businesses within India. So what is web payments? The idea is, when the World Wide Web was built, it's been 30 years, we built a lot of tooling on top of it. W3C primarily have released a lot of standards in this space. And while we have great ecosystem of tooling around, for example, email, what the web was missing so far is a standardized way to send money to each other on the internet or just pay people. And I personally believe that this has actually led to us to be lagging in certain sense on a lot of places. For example, the rise of advertising platforms within the web ecosystem is a direct consequence of the web not supporting payments. So I'm going to be talking about web payments and the web API, web payments API specifications that the W3C brings out. W3C, in case you don't know, is a standardization body that basically standardizes things for the World Wide Web, which includes a lot of standards that you may have dealt with, the HTML standard, for example, or the SVG standard, and the recent ActivityPub standards. They all come from the W3C side of things. So before we move on, let's look at a small demo just to figure out how it goes together. So this is the payment request API demo page. The way the current standard is built, it primarily focuses on card payments, but it's built generically enough to support other use cases. So this is just going to be a sample demo of what I want to buy on a website. I have something that I want to buy and I want to add, I can ask as a website, let's say this is the shopping website, I can ask for a lot of details, including my name, my email, my shipping address, etc. There's a simple call that I can make that tells me, hey, does this browser support payments or not? And am I ready enough to make this payment? Which, for example, checks whether in this use case, whether I have a card saved on this browser or not. When I click buy now, this UI that you see now is not coming from the website. This is a UI that's supported by the browser itself. This is a native browser UI. And it gives me an option, hey, I need to add a payment option. So I need to add a new card. Add a name. The UI validates things on its own. I can add a new address. And when I finally press pay, the information gets shipped to the browser itself, to the website over here. That's basically how the workflow looks like for the web payments requests API, which is the overarching API. So today we're going to, through the talk, I'm going to be discussing on how this in general works and what's the ecosystem around web payments that we are dealing with. So let's come to a bit of why. Why is this needed in general? We have been paying, Amazon came to existence in 1999 and Bitcoin exists. Do we really need something in the web payment space? The answer is a firm yes, because we want to be able to make payments in general more standardized across the internet. For example, if you go across Europe, every country has its own standard of how payments are working. India has its own list of things. For example, RuPay cards work way differently from MasterCards and Visa cards on the internet. There are similar issues. For example, we have in China, we have Alipay and WeChat Pay, which completely different in how they act and behave. Which means there's no standard layer if you are a business sitting out of India and you want to accept payments from across the world, which is a fairly common use case. And you can't do it easily unless you go and tie up with one payment partner over here, another partner over there. And finally, can we have privacy preserving payment methods? Right now, the ecosystem is built in a way which depends on what payment instrument you're dealing with, what payment processes you're dealing with. And finally, one of the major leading problems that the working group found when they decided to work on this problem was that every website had its own checkout cart implementation, which is like, hey, I'm going to website A, I'm having to re-enter all my details over again. I go to another website, and now, hey, this website also needs my card details. Can't this be made more easier? Can't I just walk up to my phone and say, hey, please buy things from website X, and it figures it out automatically? So that's the objective here. So the specification, going to the tech side, looks basically like this. There's a web payments working group within the W3C. The working group has resulted in 4 current drafts. There are a few other auxiliary publications alongside these, but the primary 4 drafts are these. There's a payment request API, there's a method identifier specification, there's a handler API spec, and there's a method manifest spec. So they broadly think of it this way. If you want to have a way to have payments working across the internet, across all payment methods, across all countries, how would you do it? It becomes a very vast abstraction problem. So this basically breaks down the specification set of specifications, breaks down all the abstractions into multiple places. So the first is how to initiate a payment, which looks like the payment request API. which basically says, hey, I'm a website. I want to be able to get money from whoever the user is. If I initiate a payment and I set certain criteria that says, hey, I'm only allowing payments within USD, or I only want to accept payments from Visa or MasterCard, or from a specific payment instrument, WeChat Pay. How can I do that? But in order for that to work, you need a way to figure out what is a payment method. So the next two set of specifications deal with that. What is a payment method? How do you define them? How do you differentiate between them? How do you standardize them so that when you're processing a card from over PayPal versus Stripe, and they both work the same way? And finally, there's a payment handler API, which is the plug and play module, which basically says, how do we process that specific payment? So we're going to be going bottoms up and seeing these specifications from the bottom up, which means we look at the smaller pieces, the payment method, payment handling APIs, and then move forward to the payment request API. And the idea is try to understand how can we complete a payment entirely from a browser without relying on any proprietary APIs, which means you don't have to, we want to deal as little as possible with a payment processor and make it as vendor agnostic. So that if I'm integrating something today, I know with a few extra changes or with the least minimal amount of changes, it should work across the world. And it should still be compatible with any payment instrument. Or I should be able to decide, hey, I want to support these 5 set of payment instruments across these 7 currencies, and it should just work. Just a note on the proprietary side of things, while this is not an actual goal for the specification, it becomes a byproduct because of how the specification is designed. So the spec does allow for proprietary places where you will have the payment processor adding in bits of the JavaScript. But as a byproduct, it becomes fairly minimal and still open to the degree because it's all auditable JavaScript. So yeah, let's start with some definitions. What is a payment method? A payment method is something that you use to pay someone else. Sounds fairly simple, but to start with, a simple payment method would be card. But do you define credit cards versus debit cards as separate? Do you define gift cards as separate? We're not sure. So this goes into the spec. Each payment method is identified by a specific payment method identifier. Payment method identifier is defined further on. I'll get to that. We have a payment method provider, which establishes the ecosystem to support that payment method. So for example, if you have a payment method called NEFT or IMPS or a wire transfer or Swift transfer, the payment method provider in this case is the issuing authority for the payment method. So for NEFT, for example, it will be the RBI, and the RBI provides the ecosystem to support that payment method in general, let's say. Then finally, to actually process the payment or to initiate the payment, we have a payment handler, which is the piece of code that talks to the payment method provider on the back end, talks to the browser in the front end, talks to the user agent, and plugs in and figures out what should be the response that gets returned to the payment request API at the end. So we'll look at these. This is very fuzzy, so let's look at concrete examples. Specific to India, a payment method would be something like a Paytm wallet account. Or UPI in general would become a payment method. Cards by themselves become a payment method. Gift card may become a separate payment method. Voucher codes, if you have them, can become a separate payment method. Bitcoin becomes a payment method. Payment method identifiers are essentially strings that identify each of these payment methods uniquely. So they can be a URL or they can be a standard string. We'll get to that. And finally, a payment method provider is the thing that's meant to be processing these payments. So it could be Razorpay, it could be Stripe, it could be PayPal, it could be NPICI/UPI, or it could be our specific bank that's processing it. So with these definitions in mind, now we understand what a payment method is, what a payment method identifier looks like, what a provider is. Let's look at an overview of how the ecosystem looks like with these specifications in mind. So going back to the specifications, the way it works is you are on a merchant website, and the merchant website, let's say, is, for example, Flipkart.com. The website is interacting with the browser in certain way. There are lots of standard APIs. You have notification API. Similarly, there's a new payment request API that the website can use to interact with the browser. The website says to the browser, hey, I want to initiate a payment, and it uses the payment request API for that. The browser, on the other hand, now has a set of standard APIs, which is called the payment handler API, which interact with a web-based payment handler. As there are some parts of it which can actually be offloaded to an actual native application. So for example, if Flipkart has asked for a payment, the payment handler API can either interact with a web-based payment handler installed by Paytm or your bank. Alternatively, it can also do the same communication to an actual installed native application on your phone. Finally, the other two sides of things, if let's say the web-based payment handler was installed by a bank, the bank handler can decide to talk to the backend server in order to determine more things. For example, if it needs to support tokenization on the bank side, or if it needs to get some critical data from the bank, see if the bank is down, see if the bank is supporting that payment instrument at this time, see if your bank balance is enough. All those checks are implemented basically in the payment handler side. So payment handler abstract out the how of the payments while maintaining the what. We have finally the browser itself will do a little bit of talking to the payment method owner. In this case, the payment method owner, let's say, is your bank, or it could be something as simple as NPCI. Basically, it's the issuing party for the payment method in general. So in the case of, for example, Bitcoin, it'll be bitcoincore.org or your the standard implementation of Bitcoin. So which installs the payment handler on the right. That was still a bit abstract on the ecosystem side. Let's talk a bit about how the flows work. So the first interaction that happens is, you go to a website and the website provides a checkout page. The checkout page goes to the browser user agent. Now the website sees, hey, the payer, which is the person trying to pay some money to the website, clicks on a pay button. The browser and the pay interact internally to decide, hey, I'm going to call the payment request API. The payment request API shows the corresponding UI, which we saw earlier, to the payer. The payer can then decide to select a payment handler. In this case, if, for example, I have multiple cards or multiple banks that I've installed as payment handlers, I can decide which one I want to support. For the specific payment handler, there's a little bit of interaction involved to decide. For example, if I have multiple cards for the payment handler, it can show me those multiple cards in case there's some extra authentication to be done. If it's a net banking payment, I would want to get redirected to my bank page, complete an authentication to some degree. All of that happens within the payment handler side. The payment handler interacts with the user PSP on the backend or the frontend accordingly. Once all this payment side is done, it responds with the data, and the payment request API gets a standardized response, which basically says, hey, this is now your payment request response, which basically tells the browser what to do with it next. The how to use this blob depends on what the actual payment method is, but it basically becomes a standardized way of keeping your credentials on the browser and making them available to the merchant website on demand. Just a note on the payment method identifiers. This is where our journey starts from bottom up. So let's say if you have a payment method identifier, which can basically be of two types. You can either have something like a URI, which will look like an actual HTTPS URI, so let's say pay.wechat.com, or alternatively, it will look like a standardized payment method identifier, which right now only supported identifier is basic card. There's work on to standardize more of these. That's basically how you differentiate how we stand. Yeah.
Dhruv, did we lose him?
No, we can hear him. Kanan, do you have a question? Hello? Kanan, we could hear Nemo perfectly. I think you, in fact.
Okay, I'll keep going in that case.
Yeah, go ahead.
So the payment method identifier is basically how we differentiate between various modes of payment, various methods of payments, right? So right now there's only one that's standardized, and everything else is basically a URI. And the URI is the one which decides how this payment is going to be processed. This payment method is standardly processed. So the next thing that shows up is a payment method manifest, which is basically the how-to action. If I were to initiate a card payment, how do I process that? If I were to initiate a UPI payment, how will that get processed? And how this gets decided is basically on the payment method owner. So the payment method owner is basically the person who owns this specific URL. So in the case of pay.wechat.com, we go to pay.wechat.com and figure out we figure out the manifest from there, and the manifest tells us how to process a WeChat payment. How do we get that manifest? We basically make a request. Let's say if lspay.com is our payment method identifier, we make a request there. We check the link header. The link header basically says has to have a rel which says payment method manifest. Correspondingly, we fetch that manifest.
Nemo,
yeah.
Nemo, your voice is clear, but your screen sharing is not happening. Can you just click on your screen again?
Just give me a second. So now, sorry.
Yeah, screen is available. Go ahead.
My bad. So just checking back. So this is how we get the manifest. You make a request. The request returns with a specific link header, which tells us where to get the payment method manifest. All right. So when I go to the payment method manifest now, if it's the LSP payment method manifest, I'll go to lspay.com/pay, whatever URI I've gotten from the link header, basically. I go over there and I get this little bit of JSON, which tells me, which is basically a payment method manifest. This is defined in the payment method specification, which says there should be two things. One is what application is going to process this, and B, where all can this be, is this method supported? So for example, a bank may want to ensure that, the payment method request API of a payment request API for this specific bank or this specific payment method should only be able to run on specific subdomains of that bank. And similarly, so if let's say Flipkart were to build a payment method, they would want it to be able to run only on the Flipkart subdomains. That's how they want to define their security boundaries. So they can do that via the supported origins. This is how the payment method manifest looks for currently Google. So if I make a request to pay.google.com/payment method manifest.json, it tells me, hey, this is my web application that's going to be used to actually process this payment. And it's currently only supported on pay.google.com. So you need to be on that URI to actually trigger Google Pay. So what happens? Let's say I'm the user agent and I found this payment method manifest, and the user has initiated a request somehow saying, hey, I want to install Google Pay, or I want to install Alex Pay. What happens? So the user agent, in this case, the browser, fetches this method JSON. It checks the supported origins, and we have the manifest. In case of, for example, if you have something that's widely supported, or you want to allow that payment method to be supported in every website, you can just mark it to the wildcard. This is how the actual web manifest for Google looks like. So when you look at Google, it had a default application which gives us a web manifest. The web manifest over here is basically comes from the W3C web manifest spec, which is basically a specification that defines how a web application should look like. So think of it like if you were to get all the metadata for an Android application from the Play Store, how would it look like? And this is the corresponding web version for that. So in this case, it wants to install a service worker, which is how the payment is going to be processed. The service worker becomes the payment handler for the Google Pay payment method in this case. So it's slightly confusing. Let's take a recap. Okay. So far, the user agent has done this. It has seen a payment method somewhere. We haven't gotten to how yet, but it's seen a payment method. It figured out, hey, for a payment method like pay.wechat.com, I'm going to go to that payment method URI, figure out if there's a link header that I can follow, or figure out if there's a manifest for this payment method. Assuming that it finds out a specific manifest, that manifest gives it a corresponding web manifest. It fetches that web manifest, and it goes ahead and installs that payment method application. By installing that application, it's going to basically install this service worker over here. It can actually, the web manifest has a lot more things. It can install, for example, notification permissions. It can install, it can ask for additional permissions. It can decide to run iteratively in the background. It'll do a lot more things. But right now, the one that's important for us is to install a service worker. A service worker, if you don't know, is basically a piece of JavaScript snippet that can run in the background and listen into events on your normal interactions with the browser. In this case, because it's a payment handler service worker, it can listen to payment handler specific API events. So once at this point, we have the payment methods application installed, which is like, for example, it could be Google Pay service workers, it could be WeChat service worker, or something else. Specifically for the use case of cards, which is what the APIs are primarily designed for. The browser is supposed to natively provide these. So in this case, there will be no additional application installed. However, the browser internally manages that. So let's say now we are going to go deeper into the service worker side, right? What goes inside the payment handler itself? The payment handler, when you register it as a service worker, it needs to provide a bit more details about how, hey, I'm going to install a payment manager and I support these specific payment instruments. So the moment you install it, if it's a bank application, it may ask you to go log into your bank website. It'll see, hey, you seem to have two different bank accounts. So I'm going to set these two bank accounts as different payment instruments that you can use to pay afterwards. Or if in the case of a browser native payment handler, it's going to say you go to the browser settings. So Firefox has one, Chrome has one as well. If you go to the Chrome browser settings and you add a credit card, it basically updates both all those credit cards or all those debit cards as different instruments over here. Each of the payment instruments can have a name, can have an icon, can have a method. A method is basically telling us which all, it's same as the payment method identifier. So in this case, it will be just basic card. And it can also be used to specify certain capabilities. So for example, you can mention whether it's a debit card or a credit card, but right now it's only used to restrict by networks. So in case a merchant doesn't want to accept, let's say, Amex payments because they charge them too much high fees, you can restrict the payments to specific networks via this. Now we are down to the service worker layer, and what does the service worker want to do? So the primary use case of service worker are three things, which is A, can I make a payment at all? So it listens to a can make payment event and says yes or no. Second, it's going to listen to a payment request event, which is when the user by interaction with the browser says, hey, I'm going to initiate a payment, and can you give me back details about how to process with the payment? And finally, if there are changes that are made to that any specific payment method, the service worker may want to do additional things. I'm going to skip this for now. But in general, for all of those specific options, the payment handler is supposed to return back a specific response, which looks like this. You'll notice that there's a lot of additional details that are not like payment specific. Why have a shipping address? Why have a payer name, email, phone? Why the method name is obvious. So these are all required, and these all were essentially in the spec because this is one of the common problems that you're trying to solve. Can you standardize the workflow for all of this? If your browser already has a list of addresses, and if your browser already has a list of your possible phone numbers, emails, and names, can it allow you to pick the identity that you want at runtime and say, hey, instead of typing and retyping all of that information over and over on all different websites, you can just pick from whatever is already saved on your browser. So think of it like a form filling plus version. Coming back to the workflow, how will it look? So far, we've seen, I have a payment application. We have seen how it's going to install a service worker. It's going to figure out the manifest. It's going to, from the manifest, it figures out what's the application to install. From that application, it's going to figure out what service worker to install. So service worker has been installed. It can also happen just in time when you initiate a payment. If a merchant decides to initiate a payment of a new payment method type, the installation of that application can happen at runtime when the payment is initiated as well. When the user clicks pay, we are going to go to true, and the payment request API UI is going to pop up, which we'd seen earlier. And the other half of the problem is here, which is on the right side, which you see 5 and 6, which is where the payment handler is going to handle the, how do I fetch the list of users? How do I fetch the list of instruments that are there? And send that back to the service worker. The service worker sends that back to the merchant website. So it's a complex flow that happens. It's like a three-way thing between the merchant website asking the browser for things, the browser saying, I don't know what all cards you have. I'm going to go and ask the payment application. The payment application can in turn decide to open a app UI in case I need to go to log into a bank or something. The user confirms the payment. Post that, I come back and say, hey, this is the thing. These are the specific payment instruments that the user selected, and I send it back to the merchant website. That's the role of the browser. So we looked at all the payment handler side of things. The final part of the puzzle comes in terms of the payment request API. So this is what, everything else so far what I've dealt with is basically an implementation detail of a payment method, which defines, if you were to come up with a new payment method tomorrow, what are the things you would want to do, or how does the ecosystem entirely work? This is the part which is going to be in control of websites. If you're going to make initiate a payment as a merchant website, if you're going to ask your users to pay you money, this is the API that you'll be using. It's a fairly simple API. It has the can make payment method, which internally calls the payment handlers and asks, can you make a payment? Can you make a payment? It goes ahead and asks all the payment methods, and you can pass in parameters to decide restrictions and say, can you make a payment for a Visa card, and so on. And once the payment request happens, it returns back a payment request data object, which comes in with all the objects, with all the details, for example, for the shipping, the billing addresses, etc. When you make a payment, initiate a payment, and you show the UI to the user, you can decide to add additional details about the payment. Alternatively, you can also decide to say, I want the user to give me a name. I want the user to give me a specific email address, or email address, sorry. So yeah, that's the overview. We'll move on to the closing things on how this is actually playing out in the wild. The first is, how do you support native applications? Most, when you think of a payment application, you think of something like Paytm or MobiKwik or Beam or UPI. And all of those usually have native applications. And the question that comes is, if I don't have a web application, how do I support this? So there are a few non-standardized changes. If you just change your payment method manifest and you specify a related application and say, hey, if other than this web manifest and this service worker that you're installing in the browser, if you could please also ask the user to install this specific application, which could be a Play Store application, it could be an iOS application, it could be an APK file, whatever, as long as the browser understands how to take an action on this. So for example, Chrome understands how to install Google Pay applications, Google Play Store applications. So it goes ahead and asks the user to install that application. And once the application is installed and set up, the remainder of the workflow remains the same, except instead of web API calls which are happening between the service worker that was installed in the browser, you now have native intent calls, for example, on Android. So the browser can make an intent to the payment application and say, hey, the user is trying to pay. Or it can make a request, can make an intent to the payment application and ask, can the user make a payment? The same API call we saw on the web earlier. You can make it over an intent instead and get the same response back. So if, for example, you haven't logged into your Paytm application, the Paytm application can return back and say, sorry, I can't process a payment right now because the user hasn't logged in. Once the user is logged in, that action returns a true instead. Let's take a look at a specific Indian example of how all the things break down. Let's say the merchant website is Flipkart. The payment application is just ICICI Bank. And you have the corresponding iOS, Android applications installed, logged in. The payment method we are going to look at is NEFT. So because it's a non-standard payment method at this point, we are going to be using a URL as a payment method identifier. Next comes a payment handler. So the first time you go and log into, let's say, ICICIbank.com, the ICICI Bank website is going to be installing a service worker on your browser that basically informs the browser saying, hey, I have a service worker installed that now supports the payment method rba.org.in/NEFT. Next, when you go to the merchant website, which is Flipkart, and you initiate a payment request using the payment request API, it's going to trigger a browser redirect. How does it know to trigger a browser redirect? By asking and saying, the Flipkart website says, I want to initiate a NEFT payment. The browser goes and asks, do I have any payment application that I know that supports NEFT payments? It finds the corresponding ICICI Bank application. It goes ahead and asks the ICICI Bank application, what do I need to do to process a NEFT payment via ICICI Bank? The ICICI application responds back and says, this is the step. You need to trigger a browser redirect. It basically just generates an HTML and says, show this HTML to the user. The HTML does whatever it needs to do. For example, in case you have multiple bank accounts, it asks you to, it shows you all the bank accounts. In case it needs to ask you an OTP, it shows you the OTP spot. You click in that. And once all of that is done, it returns back a blob of data to the payment request, to the call of the payment request, in this case, Flipkart. And then Flipkart can decide to send that blob ahead to its payment processor and take that complete the payment. And finally, a payment instrument in this case will be all the individual bank accounts that you have set up against ICICI. So that's a specific Indian example. Looking at in the wild implementations, this is like a hypothetical example. In the wild implementations, all the major browser as well as phone vendors are currently already using this for mobile payments. So for example, Google Pay uses payments API specifications heavily everywhere and uses google.com/pay as the payment method. A little bit of it is non-standard. For example, the parts where I mentioned about installing the application, but it works. Apple Pay similarly supports running in browsers using the payment request API. So does Samsung Pay. Facebook supports it within the mobile SDK. So if you are using the Facebook mobile SDK and initiate a payment from that inside the application and try to use the payment request API, it just works because it internally calls up Facebook and checks the payment methods. The payments over there happen slightly differently as to similarly for Google Pay or Samsung Pay, because they use tokenized cards, which is not part of the specification yet, but that's planned. And right now it's all a little bit of tight coupling because Samsung Pay only works when you're on Samsung Pay installed on a Samsung phone, and Google Pay only works when you are using Chrome and you are on an Android phone, and so on. But that's something that's being tackled upon. The current status of the API specification is all major browsers implement the payment request API, which is they will allow you to save cards. They will allow you to add an address. On Firefox, it's currently hidden behind a flag, but supported. Similarly, the payment handler registration, which is where the open ecosystem shows up, is currently only supported in Chrome. Other browser, and by Chrome, it's trickling down to other browsers that rely on Chrome, like Brave. But right now, it's still Chrome primarily. Hopefully, that should get fixed soon. In terms of future scope, uh, you know, there's a lot of work happening. There's most of these drafts are planned to be published as W3C recommendations, which becomes a published draft under W3C rules. Is they're mostly targeted for 2020. Let's see. But right now, installing a payment app becomes clunky. So the specification, while as supported by Chrome already, but not standardized, can be installed just a service worker. You don't need to install an actual application that shows up on your phone launcher. For example, can we just install a service worker instead? So they're looking at changing the spec towards that. A lot of work is happening towards standardization of non-card payments. So while the primary use case has been so far, how do we get this basic card payments to work while saving cards within the browser? They're looking at supporting non-card payment methods and different ways of card payment methods. For example, right now it just returns back the card number to the merchant website, which results in security issues on the merchant side. And the merchant has card numbers, and now they have to process it accordingly. Can we support tokenized cards to some degree? Can we support credit transfer-based payments? And can we support SEPA payments, which is basically wire payments for a lot of European banks? And finally, 2020, hopefully we'll get some of these drafts published as W3C recommendations, and most browsers already are implementing it, and we'll hopefully have better coverage by the end of 2020. That's it from my side. If you have questions, the reference on the slide as well. Please go ahead.
Thank you, Nemo. Any questions from folks? I have one while other people come up. You mentioned Facebook, and there you were mentioning that Facebook would usually use an in-app browser. But in a mobile phone, if I have like any other standalone app, would that app comes to like Google browser, which is installed on my phone, and then continue the payment on? Like, my question is, how would it work on a mobile phone where you have multiple apps like Amazon and this? Would that can a payment be redirected to the browser rather than doing it in the app, and then you use the web payment API?
Yes, the payments can happen entirely over the browser. However, your choice of browser basically decides. So, for example, if you're using browser X, irrespective whether it's Chrome or whatever, if you're using browser X and you have the web application or the manifest for a specific payment method installed in that browser, any payment method that supports or that's supported over there will work. If you have the card saved within the browser itself, payments will work against that card, for example. But the redirect part becomes important to support flows. For example, if you already have Paytm installed on your phone and Paytm doesn't want to give you a web application, so Paytm can install the web small service worker, which interacts with the Paytm application on the backend within your phone itself and figures out the final payment step. So both are technically supported. If you want to do a payment entirely on the browser, it is supported.
Awesome. Any question, folks? Okay, let me come to the last slide then. Let me present. Thanks everyone for staying back. Just the final feedback, and thanks for your time. We have 4 minutes before we shut down, so we wanted to get a feedback from folks on what could be the in thoughts on a future virtual event, whether this format what we had was good, was 3 hours too long, should we have at a different time? So any of the any topics. So just feel free to go to menti.com and use the code that you see 357318. Fill in your answers. These will be the feedback that will show up. So we would very instant feedback that we can get from you guys. So feel free to provide your input, and once you have done, you are free to leave. Thanks for coming. Send us an email or any of our ways if you have any topic or any speakers that you would like to present. If you had issues with the tool and you have prefer some other tools that we should use, let us know. Any of your thoughts, please go ahead, and I will let folks, once they have presented, also leave. Thank you, everyone. Thanks, everyone.
Thanks, Dhruv, for organizing this.
Thank you.
I think it worked out very well. So we should hopefully have more regular events. Because I don't think we are going to get together for a long time physically, right? So this is also a lot easier. We don't have to worry about logistics and all that. So I think maybe once in 6 weeks or so, if not 4 weeks, I think would be a good good time to have a recurring meeting.
Yeah, thanks. And other folks, you can also.
It's really good. It's really good. Good. So we'll continue this actually, because as Kannan mentioned, right, this is the mode we are going to anyway continue. So it's good to have this one.
Thank you.
Thank you, everyone.
Thank you, folks.
Thank you. Thank you, everyone.
Have a good rest of your weekend.
You too.